So some slides earlier I have already mentioned that clustering index and non-clustering index, they indeed matter if it comes to accessing sorted data. Accessing sorted data means that we want to read ranges of data. For instance, all students that have matriculation number between 100,000 and 120,000. Here you see clustering index. Clustering index means, again, that the sorting order inside the index, so the key used to construct the index, is the same that is used to sort the data file. So how can we access sorted data in this case? Well, we go down the index from the root, as we usually do when we query an index, and we go down and we find the leftmost data record with this key range that we want to search, for instance, between X and Y, that the data should be. So you would take X and walk down the tree using X, and then we come to this data entry in the leaf level of the tree, and then we go down to the leftmost entry, and then we start reading the file from this position on. Done, right? That was simple. No data page here in the file has to be accessed more than once. At some point we will stop when we have reached tuples where the condition of this range does not hold anymore. In the best case, if the data records are directly contained in the leaves of the index, there doesn't need to be any access to a separate data file be done. This was the case of the index classification in case 123, if you remember that some time ago, where the tree would not store pointers but would store directly the data records. So how does this look like for non-clustering index? Non-clustering means that the sorting order in the file is not corresponding to the key over which the tree was built. We have inside the index entries of the form key and a reference to a record in the data file. In the worst case, it can happen that every entry, every pointer here, the record ID, points to a different data page. So if we want, again, we want to have a range query, and we go down, if you have some condition that what we're searching for should be between X and Y. So you would take X again and walk down here according to X, so the smallest possible value. And then we go down, we find this leaf entry, or the leaf node of the tree. And then we start reading now the references here. And this one might lead us here. Next one here, next one there, and so on and so forth. So this means that for every data record that we want to retrieve based on the keys, we have to read one block from disk. In addition, we have to, of course, also read the data entries here, because if you have a range that is not only subsuming this node, we have to also get the next node, the leaf node of the tree, and the tree is also stored on disk, so you have additional accesses we have to pay for. Yeah? So this is like due to the fact that we don't have the same order, so we have to jump, in worst case, widely around the data file. In practice, however, the cost is a bit lower, because as you probably have already thought, it can happen that some data blocks are in our database buffer, so we don't have to read them again from the disk. For instance, if we have, I'm not sure this example has this case, no it does not, but if there's one more pointer here, then we need this page twice. And if we are lucky and this page is still in a buffer, then we don't have to go to disk and read it, right? But in the worst case, this is exactly what's happening. You have one block to read for one data entry. And that's, of course, for one data record. And that's, of course, not doable if these ranges are large. Many of these discussions, I should say, that also depends on the selectivity. That means how selective is this query. So if the range is very, very small, then using this index might be quite a good option, because then, well, we have to do some accesses to the data in a random fashion, a random access fashion, but this is still better than reading the entire file, or sorting the file and then reading sorted order. But if the range is very big, there are very many tuples, then we have to access very many data records. For each we have to read one block, and this is of course expensive. So all of this discussion depends always on what is the query, how does the data look like. But in general, we can make, of course, like illustrations or assumptions and statements that accessing sorted data from a non-clustering index can be problematic. That's important to remember. So some simple calculation. We have a non-clustering index, as you can see in the same illustration on the right-hand side. We assume we have n data pages. So these are the data pages here. We have n of them. And we have p data records per page. A data record is a tuple of a table, like some student information for one student. And p denotes how many of these data records fit into one page. So in total, having n pages and p data records per page, we have p times n data records in total. So these are the ones which are stored here inside the pages, right? All of them. And we also know, by reconsidering the B plus tree, that inside a data entry, so on the leaf level of the tree, looking at these pages here, or blocks, there's more entries here because the entries are smaller than the entries we have on the data level. Yeah, because we have only keys and pointers and not full-fledged tuples. Yeah. And this ratio we denote with f. And here we see f is 0.1, so a factor of 10. These entries in the tree, in the leaf level, are smaller than the entries in the data records, or the data pages, meaning the records, right? And then we can describe the cost for reading data records. So here on the disk, in sorted order, is approximated by p times n. And this means nothing else than we have to read as many pages. If the cost is here given in number of pages we have to access, we have to read as many pages as we have records. And this holds for small values of f, obviously, which is usually the case, and for values of p typically larger than 10. So there are 10 or more entries per data page. And that's of course not good, because we have to read many data pages, and that's not really the purpose why we should use an index if we're not gaining anything from using it. But again, often this depends in general on many factors, like how does the data look like and what is the query range we want to have, so how much data we want to read. So the previous slides had the idea, or the title of the slide was accessing sorted data. So you want to read a range, let's say between x and y, or we want to read all the tuples that have a certain value, let's say the matriculation number below 200,000. So you want to read from 0 to 200,000. If you have integers, instead of using a non-clustered index, which might not be really performant, as we have seen, we could also think about sorting the data. So we sort the data which is not sorted according to the key we want it to be. So we have our data file. Let's say it's sorted based on name of the students. And we want to read all the students that have matriculation number smaller than 100,000. So the students are located here and here and here and here and here and here and so on. And as we discussed previously, it's of course not good to use a non-clustered index, because we have to jump using the sorted order of the non-clustered index and jumping wildly around the data file. This is not good, as we have just discussed. Instead, we can say, well, why don't we just take the file and sort it such that the matriculation numbers that we are searching for, the ones between 0 and 100,000, are located in the beginning of the file, because then we can just open the file and read from it and at some point stop. In the table you see the cost of such a sorting operation, which is given in this column. N here is the number of data pages as previously, and the cost is also expressed based on the number of pages we have to access. Let's see how to interpret this. If we have 1000 data pages, and in this example we don't want to read only up to, let's say, 100,000 matriculation number, but we want to read the entire table, the entire file in sorted order of matriculation number. So everything, not only a part of it. And if we have a file which is sorted and we have a clustered index, which means the file is sorted according to the key we want. So if you have a clustered index over matriculation number, then the file is sorted based on matriculation number, and then we can just read the file and have our tuples according to matriculation number. And how many pages do we have to read then? Well, just the pages, and once only. So then that means that the cost for reading a sorted file with n pages is n. That's not very surprising, right? So you have a sorted file. Why is it sorted? Because we have here assumed clustered index. Clustered index means the file is sorted like the index. If the index is sorted based on student ID, matriculation number, then basically we don't have to read the index, but we just go here once and then we read the file. So we have to read as many pages as there are in the file, which is like, of course, the minimum we have to read because we want to have all the students, right? In this case. So how much does sorting cost? Sorting costs, according to an algorithm that is called external sort, we will have a detailed look later on. There's some parameters, of course, but detail will follow when we talk about implementation of joins and sorting. Let's just believe this is true. So sorting a file of 100 pages costs 200 page accesses. And sorting a file of 10,000 pages costs 40,000 page accesses. Of course, it's expensive to sort, more than reading only once, right? Sorting involves cost. And now reconsider the parameter p earlier that described how many data records fit into a data page, which was 1 here, 10, and 100. And here you see the cost to retrieve the data in a sorted order, like the previously described approach using non-clustered index. This was the previous slide, right? And here was the cost given. And here we see that in contrast to the cost for this non-clustered index accesses for accessing the non-sorted file in a sorted order, this is the cost. So why do I show this slide? You see here that for certain parameters which are realistic, we said p should be above 10. The cost for reading an unsorted file, or let's say a wrongly sorted file, in a sorted fashion is 100,000 page accesses for parameter 10 in the previous example. Sorting costs 40,000 only. So sorting the entire file of 10,000 pages is cheaper than using an already existing non-clustered index. Again, if this index was sorted, it's super cheap, right? As we see here. If this file will be sorted, when we have a clustered index, the cost is super cheap. But here in the table, you see the cost for a non-clustered index. And this continues, of course. Like here you have for 1 million data pages, you have a cost of 8 million data page accesses for the sorting. Compare this to 10 million page accesses required to read the same information in sorted order for a non-clustered index. And of course, if you have more data records fitting into a data page, then this cost, of course, grows. Yeah? For the unrealistic case of having data records or tuples which are so big that only one fits into a data page, then you have indeed the cost cheaper for the non-clustered index than the sorting, but in realistic cases, the sorting would be beneficial to execute, even though you have an index already on the same table. Unfortunately, here we see it's a non-clustered index, so the sorting order inside a file cannot be efficiently used to read sorted data. Again, this and previous slides were about accessing sorted data. And here we specifically talk about reading the entire tuples that we have in a relation in sorted order. Assuming that we have a non-clustered index, meaning that the sorting order of the file underlying the index cannot be used because it's sorted in a wrong fashion. And this is how much it costs to bring it to the right order. We will see later on more details on external sort and why this is so efficient. One more example on this idea, on sorting versus using a non-clustered index. Let's say we have a table with professors and we want to have those where the employment number of the professor is smaller than a certain value. In this case, the previous discussion means that it can be cheaper to sort the entire professor relation and then accessing the tuples up to this number sequentially compared to using a non-clustered index. This was exactly the motivation behind, this is a concrete example for the previous abstract examples or abstract descriptions. And now the query optimizer in the database system has to know many things in order to decide, is it really cheaper to sort the entire relation, or is it cheaper to use an existing non-clustered index? If there is a primary index or a clustered index, this would be a no-brainer because then everything is good and we can just reuse the already existing sorted file. But in this case, if we don't have the professors already sorted by ID or by this employment number, then the database system has to decide using the non-clustered index or doing sorting. In addition to all these trees we have seen now, we can also use hash functions or hash methods to create indices. And the idea is very simple. Hashing, as you know from many courses probably already, takes the space of data objects, has a set of buckets, and the hash function is used to map objects to buckets. And this is done in a way, as functions work, that if you have, for instance, here the professor ID 15 goes to this bucket, 17 goes to this bucket, and maybe 19 goes as well to this bucket here. And if you're now searching for a professor with ID 15, you will hash 15, and then the hash function will tell you, well, look here. Then you look here and you're finding professor with ID 15. If you don't find the professor with ID 15, then this professor does not exist in the database. So formally, you have a hash function h, and you have a set of keys over which you want to build the hash index using h applied on k. You go to the bucket. Usually this is also hosted on disk. And then you're inserting the tuple with this key k into the bucket. For instance, you can have some simple modulo hashing. So you have the h of x maps x to h modulo 5. And then the outcome would be, if you're applying this to a relation containing students, that here the student ID would be guiding the tuples to buckets from 0 to 4. So here's a more complex example, some more complex data we have. We have customer information, and you see here a hash function. H is used to map customer IDs to what we call a bucket directory. Bucket directory is then looked up and the pointer is retrieved. The pointer is guiding us to a block on disk where this tuple we were searching for based on the customer ID is located. So if you want to know more about Linda from Houston, we know her custom ID, and then we apply H on the custom ID, which is this one here. And then the hash function gives us inside the bucket directory a certain position where we can find the pointer. The pointer leads us to the block on disk, we retrieve it, and then we find the entire tuple describing the customer Linda. Yeah, this is how it works. So the search procedure, the cost is quite cheap. Usually it has 1 or 2 accesses only. So constant lookup cost, as opposed to the logarithmic lookup cost for trees. So we have 1 access to the directory, as depicted on the previous example, and then following 1 access to the actual file to retrieve the data record we were looking for. The performance obviously depends on the choice of a hash function, and in general, this hashing can also cause overflowing buckets if too many of the same or too many different tuples are hashed to the same location. Then these buckets get full and we have to consider so-called overflow buckets. So if too many customers by coincidence are hashed to this bucket, then we have to create overflow buckets. And now if we want to search for Linda again, and let's say Linda is placed into bucket 1 based on her custom ID, we go to the bucket 1, we read all the entries from bucket 1, and then we see that bucket 1 has also overflow buckets, and we have to continue reading. So of course the nice property of hash indices is that the access cost is constant, so O of 1. So we have 2 accesses here in this example, in this assumption. This can degenerate to linear lookup cost if these overflow buckets, or the overflow chain here, is getting longer and longer. Right? Then we have to reorganize the hash index, and we will see later on how we can come up with hash methods that can dynamically be scaled up. Because if you reconsider the simple example from before, where we have a custom ID and we say modulo 4 or 5, and then we say, oh, the buckets are getting full, we have to now have more buckets. Let's say we have now 5 buckets, and then if you can imagine by the properties of modulo that now we have to reorganize quite a lot of these tuples into new buckets, so we have to shift everything around, a big mess is created. So this was not a good thing to do, and we will see later on in some lectures later how we can have dynamic hashing methods, linear hashing and extendable hashing that would nicely behave when the data is growing. This is again summarized here on the slide, the problems if you have static hash indices. So now, having hashing as well, we can extend our view of how we can organize tuples or records into files. We had already previously seen this illustration for heap and sequential tuple ordering or sequential files. And if we have hashing, then we can illustrate it like this, that we have these blocks of similar or the same IDs within a file. Right? It's only for illustration purposes, but you can maybe remember that better like this. So now concretely going to a database system, in this case Postgres, but this is very similar or identical for other database systems following SQL standard. We have a table here, my table, with certain attributes in, and now we want to create a B+ tree index using the ID as the key. This should be our key for the index. Often this is also the key of your relation or the primary key. So now the ID should be the key, and how do we do this in Postgres or SQL? Well, we can just say create index 1, so this is the index name, on my table. This is our table name, and this is the ID of the column of my table that should be used to create the index. We can also have an index, or B+ tree index in this case, which is a composite index. We briefly mentioned this already. In a composite index, you can build indices over a set of, or like a sequence of attributes. So here we want to build a composite index on these two fields. And as these major and minor already indicate, the index, when we create it with this command here and specify the composite key major and minor, then major is the attribute which has the the main discriminative position or power, and tuples are sorted based on major and minor in a way that they are first compared by major, and only if major is the same for two tuples, then minor will be taken, right? And this is exactly how lexicographic ordering is defined. B plus tree, it says here and here and here, but does not say it in the definition or in the call of this SQL statement. This is not needed because B plus tree, at least in Postgres, is the standard index to be used. A few more words on this composite index. So we can have, as we see, indexes on multiple columns. And what is important to note, what I just already indicated by major and minor attributes in the previous example, the order in which the columns are specified indeed matters. So you have an index on 3 attributes, attribute 1, 2, 3, and then attribute 1 is the primary criterion, and then attribute 2 and so on, and we use lexicographic ordering to compare tuples. In addition to these naming of the attributes we want to have in the composite index, we can specify ascending and descending. We can also do this for non-composite indices by specifying it after the name of the attribute. So what is the consequence now when we have a composite index? Let's say we have a composite index with 2 attributes only. Let's say attribute 1 and 2. So let's forget about attribute 3. How does this look like? Well, let's say we have a B-tree index, and then at some point it always looks like this, right? And we have here, let's say, the smallest value of attribute 1, and then we have here a bunch of tuples that have the same value for attribute 1, and a bunch of tuples following that have the second largest value for attribute 1, and so on. So we have basically a group of these tuples according to attribute 1. Now within these groups, we have an ordering based on attribute 2, because that's the secondary attribute. So here, inside the blue part, we get a nice color. So inside the blue part, we have, let's say we take the green color, not to confuse with pink. So here inside the blue part, we have another ordering, which is based on attribute 2. Here in the red part, for all those that have the same attribute 1, we again use attribute 2 to sort, right? So if we have, let's say, a concrete example, we have the index is created based on the age of a person, and let's say that 25 is the youngest age, then this blue part here will correspond to all people, let's say all students that are 25. Okay, 25 is not good, students are much younger, right? So then let's say 18. So then this blue part here, the tuples, will correspond to students that are 18, and only those that are 18. Here they are the ones which are 19, 20, 21, and so on. Inside these batches of students that have the same age, we sort by name, right? So then the first tuple here will correspond to student Anderson, which is 18. The student Adam might not be in this batch because Adam is already 20 years old. So he would be somewhere later on placed here, right? This is how composite indexes work. And as we have seen, sometimes it makes sense to somehow abuse this idea of composite indices, and you're just including one additional attribute you don't really need any sorting for, And then you hopefully can, in some cases, have index-only queries where you don't have to go to the data file. But again, now to summarize this, look at this illustration, the way it's defined, and emphasize, we will also see that later on in some examples, emphasize the meaning or the idea behind the observation that the order in which you name these columns indeed matters. Yeah. Why is this? We will have an example, but now I have already drawn this. So if you have the above example with student or persons and the age as the primary attribute for our composite key and then followed by name, and we want to find all the students with name, I don't know, something in the middle, or some, let's say Smith, right? You want to find everyone with name Smith from this index. How do you do that? Where are the Smiths located in this index? Again, the index is defined by age, comma, name, right? And the ordering matters. So where are the Smiths located in the index? Well, the index is not really good for finding Smiths because where are they? Smith is a popular name, so you will find some Smiths here for this age group and here and so on throughout. So what this causes in the end is that you have to read anyway the entire data file or the entire index leaves in order to find what you're searching for. If the index would be defined by name and age, so we reverse this, then you have one group of people or students. Let's say, again drawing this, we have here all these groups as indicated above. And there's one group here, this one for instance, Smith is a bit further on the alphabet, like here. And this now here contains all the people or students that have the name Smith. And then we can go using Smith as the criteria, go down here and finding and start reading all tuples that have Smith as name. But this only works if we have name, comma, age, and not age, comma, name. So indeed that matters. To give an even more concrete example, let's consider the following query. We have some employees table, E, and we want to have the ID of these employees of those tuples where the age is between 20 and 30, and the salary should be between 3,000 and 5,000. Now, in the sense of composite indices, which index would be useful? Which composite index would be useful? You see that we have ranges for both. So we have a range criteria for salary and one for the column age. If we have an index on age, comma, salary, how would we use that? Well, we would query it based on age 20 and salary 3,000. And this will guide us our way down from the index to a certain position where everyone with age 20 is stored, or pointed to the data file where we can start reading employees with age 20. This might be leading us here. Well, and then we can start reading, and from the employees records we read then, we have to get those where also the second criteria, so the salary, is matching. So it's okay, this one is useful. And the other way around, having salary and age, well, then we take our index and we query it with the query 3000 and 20, so the other way around. Again, this will lead us somewhere. This will point us to a position in our data file, and then we can start reading, and we will read here people that have 3,000 salary. And within these, we have to pick out the ones that are between 20 and 30. So in this case, both orders would work, so there's not a difference. Yeah, it's kind of clear because we don't make any difference here in the query predicate. They both have both age and salary have a criterion on which includes a range, right? So we would not really see a difference here. In general, to say that again, the order matters. In this case, at least from looking at this description, without knowing any more details, both should be the same in terms of usefulness, but it always depends also on the selectivities, how many people have an age between 20 and 30, and how many have a salary between 3,000 and 5,000. If most people have a salary between 3,000 and 5,000, then an index on salary, age is not as useful as an age, salary index, right? If you reflect what that means. Here we have a query, a similar query on employee table, and we want to have those that have age 25, and the salary should be between 3,000 and 5,000. Yeah. So looking at composite indices, which index would work very well here? Well, composite index has two attributes inside as by the definition, and the first one is the most important one. And if we use age salary, so age as the major attribute, then we will have an index where at some point we find tuples with age equals 25, so a block of them. Well, then we can read them and find out from the tuples we have seen those that have salary between 3,000 and 5,000. So this would be useful in this case. If you have an index defined on salary and age, then we can query it with the query 3,000 and 25. But in this 3,000 to 5,000 range that we somehow can retrieve, only a few will be the ones we are searching for, because perhaps only few, or we have to find only the persons which are exactly 25. Right? And just by making some assumptions, reasonable assumptions, this might not be as efficient as the previous case. But again, these observations or the discussion always depends on the selectivity. If we have a company with very young people and they're almost all 25, this might not be as described here, right? But in with reasonable, these are only examples to emphasize what is effective in general and what is not so effective. You can always tweak the data to say that it's not true and the other way around holds, but for normal assumptions, these examples should make sense. But again, it always depends on how many tuples you have within the range or within age 25 and so on. Right? So this needs to be also said here. Hopefully this doesn't sound too confusing, but I guess the example makes sense. But you also understand that if the data has some weird characteristics, then this also might not be true what is written here, right? But let's say data is well behaving and also what we assume from a company, and then this could make sense, right? If we have a query now and we have only the range on the salary as the criterion, so we eliminate this part. This was too much. We eliminate this part here. Then, of course, the index on salary, age would make sense, because then we would come here indeed to these green ones that have a salary larger than 3,000, and then we don't care because we don't have any criterion on the age. We would just read the entire data and we're happy, right? So this changes a bit the picture. When we modify this example and we want to not have the IDs, but we want to have the average salary, then we come back to what we have seen some slides earlier, where we called an index-only query, because if we have an index on age and salary, then this query can be answered without looking at the data. It can be answered only by looking at the index. Yes, this would also be possible to answer using salary age. But again, for reasonably well-behaved, let's say realistic, real-world data, normal companies without any weird age distribution, salary age would be more costly than age salary, the indexes that we have created. So we did not say anything about having hash indices in Postgres. So here it is how you're creating them. Since B+tree indices are the standard indices in Postgres, here if you want to have a hash index, we would need to write using hash. In general, hash indices are used only for point queries. There's no, at least no direct way to answer range queries using hash. That means comparisons like this, want to have everything between 20 and 50, or comparison operators for the queries are not supported by hash indices. Only this a equals x is supported. In Postgres, also algorithmically there should not be any problem. In Postgres, hash indices only support single attributes. So you cannot have composite indices using hash. So why is it is not possible to have range queries or comparative predicates? If you see or recall again how hashing works, you have a hash function and you're mapping 15 to some space, right? So modulo or some other hash function. And then in general, it is not possible for every hash function to support ranges because 15 might be hashed to this bucket and 16 might be hashed to another bucket and 17 might be hashed to another bucket. So what does it mean now if you're searching for all tuples that are between 15, 16 and 17, so between 15 and 17? Well, this means that you have to look here and here and here. It is not possible in general for this modular hashing or other simple hash functions to hash 15 to go here and then need to read neighboring hash buckets because there are very many hash buckets and you care for these light blue ones only. So you don't want to read them and you don't want to read them. You want to read the light blue ones. And you cannot read just this one for hash of 15 and then start reading. This will lead in this example to reading the entire file. You don't want that. That's a general problem of having hash functions or hash indices in a database. The use of them is very restricted. They are very good for point queries, but not applicable to range queries. This also will play a role in the end for index tuning when you want to decide which index to create. If you're not sure what kind of queries you have, if you also would have, or in the end up with having range queries, then creating a hash index is not good. You should create a B+tree index if you're unsure, because B+tree indexes are more flexible. Yeah. So again, this is the syntax you used how to create hash indices on your table. There's no possibility to have multiple attributes, only one attribute, and this works only for point queries, where you have equality to a certain numeric or string value.